Friction is due to the interlocking of molecular hills and valleys between a surface and an object on the surface. Even if you look at your lab tables, for example, they may seem smooth to your eyes, but if we were to zoom in on the atomic level, we would notice that actually they were very bumpy, and you have two bumpy surfaces sliding by each other, and the bumps catch with each other and apply a resistive force. And the key idea with friction in terms of direction is that it resists sliding. Which way are the objects sliding relative to each other? Friction will act in the opposite direction. And because of that, it can resist motion, like when you're trying to slide furniture across the room. It can also create motion for walking or driving. Example 1 says, draw the direction of friction in each case. You might be able to see a tiny gap in your handout. That tiny gap shouldn't be there. That's just Word being fussy, and I couldn't quite nudge the drawing down, so just pretend it's not there. If we were sliding this object to the right, which way would I feel friction resisting me? Yes. I abbreviate friction as a capital F and then a subscripted FR. I don't know why I put the R there. If you put F like that, I'll figure out what you mean, and every textbook does that. This might be, Vanessa, the only time that I put an extra letter that's unnecessary, and I don't know why, but for 20-odd years, I've just done that. The force of, for some reason, my brain just puts the R there, and it's a habit, and I can't resist. So F, friction, force of friction. Now, why is that? The object is sliding forwards relative to the ground, so friction will be backwards. Compare that with a car speeding up. With a car speeding up, the tires right there are pushing backwards. Don't write that down, just watch. The tires are pushing backwards. Forces come in. So the tire applies a force to the road. What does the road do? Apply a forwards force to the tires. So in this situation, friction is pushing the car forwards, not backwards, not slowing it down. And it's because if you zoom in, the tires are actually trying to push backwards, and so the road pushes forwards. It's actually the opposite of this picture right here. But just that right there, Oscar, that explains why it's so tough to drive on ice. You think tires are what makes the car go forward, or the engine? You have both of those on the ice. If tires or the engine were what made a car go forward, then you could drive on ice just fine, because you still got your tires, you still got your engine. What's changed? Less friction force. And when you're slowing down a car, when you press the brakes, you might think it's the brakes that make you stop. No, it's not, because if the brakes made you stop, we could put you on ice, you'd still have your brakes, you'd be able to stop. When you hit the brakes, what you really do is you get your tires to apply a backwards force forwards against the road. Forces come in, and so the tires apply a force forward on the road. What does the road do? It applies a force backwards on the car, and that force, because the tires are trying to slide past the road, that force is friction. What if there was no friction? Then objects on land would move like objects do in outer space. They would keep going in a straight line at a steady speed. If there was no, you know what? A picture's worth 1,000 words. Put your pencil down. So on the next page then, how do we calculate friction? What does it depend on? It turns out it depends on two things. The first thing friction depends on, especially based on the video that you saw, is how slippery objects are. Or, if I take the opposite view, how sticky objects are. We have a number and a symbol that we use to describe stickiness. It depends on the type of surfaces that are in contact and how slippery or sticky they are in relation to each other. This level of stickiness or slipperiness is called the coefficient of friction, and it has a Greek symbol, the Greek letter mu. Looks like this, folks. This is a Greek letter mu. What does a Greek cow say? Mew. What does a Greek cat say? Mew. There's a whole bunch of stupid jokes. So it looks like that. It sort of looks like a lowercase m with the long arm. So what was that?
Is that your good one or no?
No. That wasn't my good joke. That's not till next week. And again, it's not good. It's so bad that it almost approaches good. So mu, the coefficient of friction, has no units. It's not a force. It's just a number that we attach to describe how sticky something is compared to something else. Typically, it's a decimal between 0 and 1. So steel on ice is about 0.01. Teflon is near 0. Glue would be over 1, and there are situations where you can have a coefficient of friction bigger than 1. But for example, rubber on concrete is about 0.75. That's why we make our tires out of rubber. So one of the things that friction depends on is mu, the coefficient of friction, how sticky stuff is relative to the other object. There's a second thing that it depends on as well. I got to pause the video for a second. So friction depends on the coefficient of friction, and it depends on the force pushing the surfaces together, which in really basic questions would be mg, but this is not always true. A better descriptor would be to realize it depends on how hard the ground is pushing up, and we give that force a special name. It's the normal force. Here is your final equation for this unit. Friction is equal to mu times the normal force. And if you look on your formula sheet, you'll see that's the last forces equation. There's one line on your green sheet that starts out with F net equals MA. And then I think in the middle it says FG equals MG, and then in brackets the word weight. No, now. And then right after that it says friction equals mu times the normal force. And that's it, which is one of the reasons why, Kyle, I said this is a tricky unit. I'm not giving you a whole bunch of equations. You're inventing the equations by using a free body diagram and Newton's laws. Friction is what times what? It's mu times the normal force. Friction is what times what? It's mu times the normal force. You don't need to memorize that, but most of you will because you'll get sick of looking it up, and I'm good with that. So, I like example 2, I like example 2, I like example 2. Example 2 is the next question. Suppose we're pulling on a 6.5 kilogram mass across a rough surface at a constant speed. How hard do we need to pull? First of all, what 2 words should I mentally underline that are probably the key to doing this whole question? Let's do that in our notes so that we know we paid attention. If you don't underline it in your homework, but you just mentally tag it, I'm fine with that. What's it asking us to find? And you know what? I think that's going to be this here rope force here. You know what this is a good job for? Now, how did I know to do that? This is important because I've told you if it says F net, you can go straight to F equals MA. But the reason I really knew, they're asking me to find this force, and the fact that they said rough and gave me a coefficient of friction, there's friction. If there's more than one force, that's a job for a free body diagram. Except, Ryan, it's not. It is. I could, don't write this down, represent the mass with a dot. But did they give me a picture? I'm going to be lazy. Rather than do a completely separate free body diagram, I'm going to slap the forces on this picture, which technically is not a free body diagram because, Matt, you're supposed to represent the mass with a dot. Blah, blah. You know what? Let's label our forces. What are the forces acting on this box? Get the obvious one. mg down. Is this box sinking to the ground like quicksand? Is it flying to you like Superman? So in the vertical direction, the forces must be... In other words, everything up equals everything down. So I know there's an arrow pointing up. What force is that? That's, we've reasoned, is what we call now the normal force, the ground pushing. It has to be there because of Newton's first. And I drew my arrow about the same length as mg. What else? Well, there's this mysterious pull. I guess since it's a rope, I'll call it, you know what? Put a capital T there, tension, or put an F there. I don't care, whatever you want to call it. What else? Is there friction in this question? Yeah, because they said rough surface and they gave me a coefficient of friction. They told me how sticky the ground is. Which way do I think this block is sliding? So which is friction going to be pointing? Bigger, smaller, or the same size as tension? What two words did I underline? So that means the forces are, I'm looking for the letter B, bigger, smaller, or the same size as tension. Yeah. See it? What equation pops out of here in the horizontal direction then? Normally I would say, who's winning? Who's losing? But in this case, I think it's a tie. If it's a tie, what does my equation become? I'll give you a hint. Tension equals friction. By the way, you could go tension minus friction equals 0 because it's not accelerating, and m times 0 would be 0. But can you see, you would just plus the friction over to this side, and lo and behold, you'd end up right there anyways. So friction is what times what, William? Friction is what times what, William? And that's how you're going to say it. And I'm going to come back to you about 60 times on that in the next 3 or 4 days. That's going to be your cue. So you ready? Remember? Okay? Yeah? Good. So William is correct. By the way, my other two classes, there was dead silence for like 60 seconds, even to the point when I said to them, can you go look in the box right up? And they would look in the box right up there and drool would fall. So thank you for getting that right away, William. I appreciate it. So you said mu times the normal force. I agree with that. Problem. Here's the problem. I don't know the normal force. Oh, but look. I know another force the same size as a normal force from my free body diagram. Which force has to be mathematically exactly the same size as my normal force from my free body diagram? mg. You're never going to hear me say friction equals mu mg. Today, it will usually end up being that because mg and the normal force will be the same. That'll change next class. So don't think to yourself, oh, friction equals mu mg. I'll snap. I'll lose it. I'll go cuckoo for Cocoa Puffs. Friction is mu times the normal force. I don't know the normal force. Oh, but look. I know the force the same size as the normal force. So I can now say, William, my friend, tension equals mu mg, which is friction equals mu times the normal force in disguise. Hey, folks, what's mu? I don't know. What's mu with you? What's mu? 0.64. And the mass is 6.5. And G is 9.8. How hard do we need to pull over this rough surface that has a coefficient of friction of 0.65 if we want to keep this thing going at a constant speed? What do you get? Doing this very roughly in my head, it's in the high 30s or 40s, I think.
40.76.
Let's go 40 point. Let's go 3 sig figs, 40 point. By the way, technically I should go to 2 because of the 6.5 and the 0.64. And so if you said 41, I'd say yeah. And I might do that on an answer key without thinking about it. But 40.8 is pretty good. Units, it's a force. Newtons. Turn the page. By the way, we give a special name to an unknown mystery force appearing from an outside source. We call it the applied force, and we often symbolize it with F and a subscripted APP. I like example 3, I like example 3, I like example 3. Example 3 is a nice question. Chelsea, what are they asking me to find in example 3? Yeah. You know what this is a good job for? Now pause. You realize now I think we have 5 different ways to find acceleration. How did I come to that free body diagram so fast? I thought, well, VF, I don't see any of that anywhere. I don't see time anywhere. I said, they gave me an applied force. Friction is mentioned. Is there more than one force? This is a job for a free body diagram. Okay, that all boom, 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 boom in my head to make that decision. Okay. Although, since they gave me the picture, Chelsea, do you mind, rather than doing a proper, complete, separate free body diagram, I'm just going to label the forces on here. Hey, Chelsea, what are the forces acting on this box? Get the obvious one. Yep. What else? Yep. And this is why I say go systematic, because have you written something down? You got the mental juices flowing. You feel better? Good. What else? Well, this question mentions an applied force. So I'm going to draw an arrow like this. I'm going to call it F applied. And I can even tell you how big it is. It says that it is 86 newtons. I'll stick that on there just for giggles. I typically save friction for near the end because often I can figure out whether I'm drawing friction bigger, smaller, or the same size by saving it until the very end. So, what else? Friction. Which way would friction be pointing? Well, Chelsea, it depends. Which way is this object sliding? I'm not sure. Which way is it probably sliding? Yeah, to the right. So which way would friction probably be pointing? Let's go with that. And I think it's smaller than the applied force, but I'm not quite sure. Mr. Dueck, I want to know ahead of time. I'll show you. There's a simple test along the way where it will become obvious if we've guessed wrong. If instead of speeding up to the right, if it's slowing down and moving to the right. Who's winning? Who's the loser? Kyle, did you see? I said, who's the loser? And she looked at you. Oh, that's horrible. I'm going to have to clearly phrase that differently. Who's the losing force, Chelsea? That's what I meant. Jeez. That's not my best dumb joke on it.
I know it's not.
Okay. What does winner minus loser always equal? Yep. What's this question asking me to find? How would I get the A by itself? Okay, pause before you do that. Now that I've done this line right here, stop. I would also have no problem giving you the acceleration and the friction force and saying, find how hard we're pulling. Find the applied force. How would I get the applied force by itself? Plus the friction over. I would also have no problem giving you the applied force, giving you the acceleration, and asking you to find mu, the coefficient of friction, hidden in here. And we'll do one like that later. But I think I mentioned the other day, we're at a stage now where once I show you the basic first step, Matt, going backwards or forwards, I think is fair game now, as long as I give you every other piece of information. But how did you say we're going to get the A by itself? Do you mind? I'm just going to do that. I'll get A equals, the applied force is 86 minus, William, friction is what times what? Good. All over M. Uh-oh, problem. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Which force is the same size as the normal force? mg, you say? So if I hear you correctly, Chelsea, you're telling me that it's going to be 86 minus mu mg over m? Don't try and memorize this equation. We'll derive it because it's going to change if I change the parameters anyways. Okay, let's plug and chug. It's complicated plug and chug, but it's still plug and chug. It's going to be 86 minus, hey Chelsea, what's mu? I don't know, what's mu with you? What's mu? What's the mass? Good. G 9.8 all over 6.5. Is this a fraction? Is there more than one thing on the top? I'm going to ask all of you to try typing this in, because this is one that drives me crazy. I see time and time again on a test, kids get to this line, and then they get the wrong answer, and it drives me crazy. This is about where my ability to do math in my head breaks down. I have no idea what the answer is. I mean, okay, it's going to be roughly 90, take away roughly 30. I have no idea. 1 point something, 2 point something-ish, maybe. Oh, I'm way off. Sorry, 6.9. You rounded off properly this time. And it's an acceleration, meters per second squared. Now, there's another possibility. We could have got exactly 0 as an answer. What would that mean? It's moving at a constant speed. It's a tie like the last question. The other possibility, Chelsea, is you could have gotten a negative acceleration on your calculator, and it would stand out. It would catch your eye. You would, what? What that means is actually friction is bigger than the applied force. You did the question wrong. Start over. Who's winning? Friction. Who's losing? F applied. That equals MA. But it's a pretty easy fix, and it catches your eye. Example 4. Suppose we're pulling on a 6.5 kilogram mass across a rough. The homework is going to be every question, but I'm going to be giving you some time on Tuesday. Tuesday, we're going to be watching a Mythbusters video, and then you'll have the rest of the class to work on the homework. Suppose we're pulling on a 6.5 kilogram mass across a rough surface with a force of 48 newtons. What will happen? This is really asking, I guess, will it accelerate or won't it? I don't know. You know what this is a good job for, Matt? And if it will indulge me, I'm going to do the diagram right on here instead. Matt, what are the forces acting on this? Get the obvious one. What else? Same size. What's going to happen, by the way, next lesson is I'm going to have other vertical forces the same way I had August and Logan push down or lift up, and that's going to mean the normal force is not going to be mg. We'll have to calculate it first and then keep going from there. Okay? It looks like, Matt, we have this mystery applied force, and it even says it's 48 newtons. Is there friction in this question, Matt? Say yes. How do I know? They either say the phrase rough surface, or they actually give me a coefficient of friction in the diagram. That's also, often you'll see they'll put a little mu equals 0.36 or something right in the picture, right where the two objects touch. That's usually our way of saying, hey, include friction. Which way would friction be acting? If we're sliding to the right, and let's assume we are, okay. And let's assume it's smaller. I drew a smaller arrow than F applied, but I'm not sure. Matt, who's winning? So first of all, folks, vertically it's a tie. Yes? So we're doing a horizontal equation. Who's winning? Except I didn't call it the rope. What did I call it? Which stands for F applied, or the applied force. That's going to be our generic, something's pulling. Could be a little invisible leprechaun. I don't know, but something's pulling. Who's losing? What's that always equal, Chelsea? You're back now, right? Okay. This question I would never put on a test because what will happen to me is too vague. I think I'm going to try and find the acceleration. How would I get the A by itself, Matt? Divide what? Let's use nouns and not pronouns. I want the A to stay there. So what do I want to move over? How? Yeah, divide the M. And the reason I'm fussy is I always have some kids, divide the A. No, I don't want the A on the bottom. That's the worst place to have something when you're trying to get it by itself. Blech. And I get this. A equals F applied minus, hey, William, friction is what times what? All over M. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Which force is the same? Oh, my laser pointer's dying. Oh, there it is. Which force is the same size as the normal force? mg. So I can say, and some of you are saying, hey, Mr. Dueck, this looks really similar to the previous question. Algebraically, it should look the same. I can say F applied minus mu mg all over m, where F applied was 48 minus, hey, what's mu? I don't know, what's mu with you? Is it 0.64 again? Same surface. M, 6.5, G, 9.8, all over 6.5. What do you get? $1.11. Anybody else? Positive? So the fact that it's positive, I guessed right on the winner. And it is accelerating, not as much as last time. 1.11 meters per second squared. Next page. It's time for a thought experiment. And once again, we're going to get to vote. How high you hold your hand up is how sure you are of the answer. So here's the thought experiment. It says this. A student gives an old shopping cart a big push on a flat, rough surface. When I say rough, what am I trying to hint to you? Include friction, please. Which of the following 4 free body diagrams is the correct diagram for that situation? You know what? Put your pencils down, look up. So we got 4 choices. The cart is moving to the right. Who says A is correct, Mr. Dueck? It's got to be A. A. 1, 2, 3. Oh, I'm going to have a little controversy here. Who says it's got to be B, Mr. Dueck? B. Obviously, B. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Cole does the peer pressure vote. 11. Oh, 12. Okay. Who says C? Who says D? You know, let's use a process of elimination. Rather than picking the one that we know is right, let's see if we can reject some as they must be wrong. Which way was the shopping cart, and when I did it with the office chair, which way was the shopping cart or the office chair traveling? To the, looking forward being letter R, to the right. Were they speeding up or slowing down? So which way were they accelerating then? That's the big question. If we're moving right and slowing down, which way are we accelerating? To the left. Which way are we accelerating? To the left. Which way are we accelerating? To the left. Is picture D, is it possible for that one to be accelerating to the left? In fact, that would be speeding up. Is picture C, is it possible for that one to be accelerating to the left? That would be going in a straight line at a steady speed, maybe. Picture B, the one that most of you picked, is it possible for that one to be accelerating to the left? Do I have an unbalanced force pointing to the left? Either these are equal, which means it would keep going in a straight line at a steady speed, or if I took my ruler out, I might find this one was a bit bigger, in which case it's speeding up. It can't be that one. The only one where we are accelerating to the left is A. And well done, the 3 of you that selected it. Okay. Those of you that picked B, you fell into a classic physics mistake. You're mixing speed with acceleration. You're mixing velocity up with acceleration. Newton's laws do not tell us anything about velocity. They tell us the direction of the acceleration. And that's why you heard me say, which way is it moving, speeding up or slowing down? Which way is it accelerating? That I can work with. By the way, what law did I use to answer this question? No? Okay, then we'll have to write it out. If we wrote it out, we would say A is the only picture with an picture, Mr. Dueck. Wait a minute. FBD, why don't I abbreviate, with an unbalanced force slowing it down. I would have just said Newton's first, drop the mic and walk off, but since nobody here could remember that, I guess you need to write out the verbal explanation of what Newton's first says. Don't feel bad that most of you got this wrong. Warning, I'm going to get you a bunch more times this unit, and if you take Physics 12, there's a demonstration that I do in Physics 12 that I've been doing for going on 10 years now that not once have I had a single kid get it right yet. And in fact, that demonstration fooled a room full of physics teachers, including myself. Newton's laws are not intuitive. How unintuitive are they? Right now, on the Government Ministry of Education curriculum, in grade 6 science, teachers are supposed to teach Newton's laws, except the curriculum is wrong. The curriculum says, and I quote, discuss how balanced forces can cause motion. Can balanced forces cause motion? No. But that's on there, and that's what grade 6 teachers are teaching their students. Right now, the BC Association of Physics Teachers is trying to get the government to change it because it's wrong. We have people with their PhD in physics from UBC and UVic and SFU trying to explain to the Ministry of Education, I'm sorry, Newton's first law says exactly the opposite. Balanced forces cannot cause motion. If the forces are balanced, you're either going to stay at rest or you're going to keep going in a straight line at a steady speed, but you're not going to cause anything. No luck so far. I like example 6. I like example 6. I like example 6. Example 6 is a nice question. Kedra, what am I asking you to find on example 6? Hey, what's mu? I don't know. What's mu with you? Yeah. So I'm going to get the mu by itself eventually. Mu appears in friction is what times what, William? Did you say mu? Okay. And this is how my brain would think. I also see an applied force. There's more than one force. What's this a job for? Free body diagram. That's how I put all that together. Okay. Except, did they give me a picture? I'm going to label the picture. What are the forces acting on it? Get the obvious one. What else? Same size as mg. What else? Come back to friction, but I see the applied force. What I often do is, just so it stands out, I'll put a little pencil or pen arrow on the arrow so that I don't forget it. Or you could even draw a completely separate arrow, something so that there's no way that I'll forget the 12 is there. What else? And I think that way, because I think those little 2 lines are supposed to indicate, ooh, speeding to the right, movement. Oh, and I also know, because they did tell me there's an acceleration. Who's winning? The applied, the 12. So let's go. We have, in fact, you know what? I could even put a little APP as a subscript underneath the F right there, and I'll end up with F applied, who's losing, minus friction, and that equals what? MA. William, friction is what times what? So my next step, I would drop the F applied down like a domino, and I would replace friction with mu times, hit the wrong button, Mr. Dueck, the normal force. See it, Kedra? Yeah. Kedra, what's immediately in front of the mu that I don't like? The subtraction. Swappy dance. I'm going to plus this whole thing to there. At the same time, I'm going to minus the MA to here. That'll give me a prettier equation. The F applied drops down like a domino, but I'll have minus MA. That equals mu Fn. And now, no dumb negatives to make silly mistakes with or anything like that. What am I trying to find, Kedra? Hey, what's mu? How would I get the mu by itself? Divide the normal force. So are you telling me that I would go boom, and then I would do this? Yeah, I would too. Oh, wait a minute. I don't know the normal force. Oh, but look. I don't know the force the same size as the normal force. Which force is the same size as the normal force? I have no idea what you're saying. Look at your free body diagram. Which one must be the same size? mg. Okay, I know where we're going now. So if I hear you correctly, you're telling me that mu is going to be the applied force minus ma all over mg. Are you going to be foolish enough to try and memorize that equation? Oh, I hope not. Are you going to be clever enough to learn to derive these from scratch? It's a better way to be. What was the applied? 12 minus 5. What was a? 0.8? I've scrolled down. What was the acceleration? 0.8. All divided by 5 times 9.8. Pedra, is this a fraction? Is there more than one thing on the top? Brackets around the top. Is there more than one thing on the bottom? Can all of you practice typing this in, please? And I'm hoping you get a decimal between 0 and 1. And if I'm running the numbers in my head really quick, I think you'll get something in the 0.1, 0.2, 0.3 range-ish. I hope. Or I could be totally off. Haley nodded. What'd you get? 0.163? Anybody else? What does that tell me? Fairly slippery. 0.163, it's about like a wet floor in our hallways where they put up the yellow sign. And by the way, the yellow signs, of course, really what they should say instead of wet floor is small mu. Because that's what's changing. What's changed is the coefficient of friction, right? What are the units for the coefficient of friction? There are none. All it is a number ratio that describes how slippery things are. How slippery are these? About a 0.163. Not newtons, it's not a force, no units. Is that okay? Your homework is, but I'm going to give you about, I hope, 25 minutes on Tuesday to work on this too. On Tuesday, we're going to be watching a very, very famous physics myth on Mythbusters. I'm also going to be giving you a bonus challenge where if you achieve the bonus challenge, you can get 2 bonus marks on your forces test. And you can probably make about $100 in your lifetime in bar bets. Probably. Put your pencils down. Look up.